My name is Pete Fletcher, and I am a technical marketing architect at VMware, focusing on virtual volumes and vSAN.
I'm Patrick Dirks. I'm a senior manager in core storage, and I manage a team that's responsible for, among other things, virtual volumes.
Yeah. So thanks for coming. You know, it is Thursday. Usually when I get a session assigned on Thursday, I'm like, oh, great, it's going to be me and about 4 people. But this is a great turnout for a Thursday, so I appreciate that.
Yeah, it's besides the chance to talk one-on-one with customers, getting a chance to go deep dive on vVols is always the highlight of my VMworld. So
yeah, for sure.
Happy to have you here.
Patrick and I have been presenting vVols for a couple of years now. I'm the pretty face, and he's the really smart guy, so I think we make a good team.
He's the generous one.
But yeah, disclaimer, I think you've seen that already. Storage is hard. It really is. I mean, half of the room will say it's not hard, it's really easy. And the other half is going to say it's extremely hard. But, you know, it doesn't have to be hard. I'd say probably not hard, maybe more tedious, right? Unnecessary. But it really, again, it doesn't necessarily have to be so tedious. I think that was one of the primary goals of virtual volumes initially, was to sort of make storage more software defined in essence. You know, virtualization came after storage. And so, you know, some things were forced fit into storage to make it work, you know, like creating LUNs and statically assigning them and creating IQNs and stuff. And so things just got super complicated. Certainly it works, and a lot of people make a lot of money managing storage environments, but it really, really, really doesn't have to be that hard. And I think that's one of the main goals of virtual volumes, is to, you know, radically simplify the process, whether it's the day 0 process, the day 1, and the day 2 operations. And so today we want to talk about how virtual volumes addresses that by at least identifying some of the pain points of virtual volumes. The first one I would say is siloed management. You know, you're a virtual administrator, you're in vSphere, great. Maybe you're the storage administrator and you're just managing your hardware array. But really quick, how many folks in this room are virtual administrators? A lot of folks. Excellent. It's a good thing you're at a virtualization conference, huh? How many storage administrators are here? Okay. Now the big question, how many are both? See, that number keeps getting bigger all the time, right? Yeah. There was a time when it would be half the room was virtualization, half the room was storage administration. But yeah, everybody is now becoming both, no matter how big the company is, or at least the teams are.
And the good news is virtual volumes are useful for both parties, so
absolutely,
we'll try to make sure to highlight that.
Absolutely. So yeah, the whole single pane of glass, right? So no one wants to have to constantly be going back and forth through a storage array software, then going back into vSphere. So definitely there's some challenges with siloed management. But the bigger one, I think, is the rigid infrastructure of traditional VMFS environments, having a LUN, connecting it to a data store that has very statically assigned, pre-allocated space, you know, very specific classes of service tied to that individual LUN. And then when it outgrows the space, you have to get another one, and you have multiple, and then there's LUN sprawl, and it just becomes really tedious unnecessarily. And the last one is complex processes. Having to manage Excel spreadsheets of LUNs, trying to figure out, hey, does this LUN have, you know, replication? Is it spinning disk or is it flash? Is it replicated? And just not having that visibility inside of vSphere. So having to manage things from different places. I would definitely not say it was simple. And so these are the things that Virtual Volumes has been preaching for the past couple of years about how, you know, it makes it simpler. But, you know, is everybody diving into virtual volumes? Well, no. At first, it took a while. It's been around for 2 years, and the adoption rate was initially pretty slow. And so, you know, but we had to think about, like, well, why is that? And the biggest reason is 3 words: array-based replication. A lot of companies would come and talk to us and say, this is fantastic. I cannot wait to get the improved performance, the way we offload snapshots, the way we can instantaneously do clones and not have to do VMFS snapshots. I love the idea of not having to manage 2,000 LUNs. You know, so like the idea was great, but if I can't replicate it, it's not enterprise ready. That was kind of what we've been hearing for the past year. And so we were pretty excited about the fact that now it is enterprise ready with the support for array-based replication. And so it's fitting into a lot more organizations now. So the big question comes up, well, what about the adoption, right? We hear that all the time. Give me some use cases, give me some examples. And I can't give you exact numbers of adoption. The product manager is a little stingy on that for now. But I will say the big curve here, if you look on the bottom, vSphere 6.0, you know, it was a slow grow for a while. But the minute we had 6.5, you know, adoption, which was the version that has array-based replication, we started to see a dramatic increase. And very large environments, petabytes and petabytes, actually using virtual volumes, not just clicking a box and trying it, but really using virtual volumes. And so the level of adoption is aggressively rising.
It makes sense because in very large environments where you're managing, hundreds or even thousands of LUNs, is exactly where virtual volumes, being able to consolidate down to a few storage containers, makes a lot of sense. And automating it with storage policies, as we'll see, makes a lot of sense for large environments. So
absolutely. So today we're going to talk to you a little bit about vVol architecture. Pat's going to walk through that and show you some of the differences, identify some of the pieces that you might want to consider. We'll talk a little bit about how virtual volumes is simpler, smarter, and faster. And then we don't have a demo, but we can maybe demonstrate physically and do a dance or something. And,
how about we just leave extra
I'll be a virtual volume, and then you can,
Or maybe we could just leave extra time for Q&A.
Yeah. Our demonstration is going to show you how we can perform Q&A. So with that, Pat, let's talk some architecture.
Great. So before we dive in, and this is after all a deep dive, a heads up, we're going to cover a couple of really basic building blocks, but they will all come together. And by the time we're done, you should understand how vVols works and how it can help you better manage and consume storage in your environment. And with the understanding of how it works, what to look out for with your particular array in your particular environment to make the most of vVols. So with that, here's the big picture. The main things that virtual volumes introduces that may not have been there before is this VASA provider. And we'll talk about that in a little bit. But virtual volumes, if you remember nothing else, virtual volumes introduces virtual disk objects as first-class objects on the array. And the data path to those objects stays the same, but the management is now done entirely through this agent that the storage array provides. So these virtual volume objects are entirely owned and operated by the array. vSphere has nothing to do with it except what happens through this VASA provider. So these virtual volumes are native on the array. There's no file system imposed on the array or anything like that. And we'll see how that's an advantage in a little bit. That VASA provider is custom to the array, and it tells vSphere everything about the array, the capabilities of it, what protocol endpoints there are for the data path, everything about it, the storage containers that exist, the limitations that are applied there, everything. And these capabilities are one of the reasons that that virtual volumes let you automate the storage consumption so nicely, because these let you create storage policies that then become the SLAs for the objects that you create, but they're explicit. It's not just because you happen to pick the right volume out of the spreadsheet the first day and placed it there. If a year later you need to go back and look at something, you can look at the storage policy that was associated with it, and it'll spell out what the SLA is that's needed for that object. And that's actually something that you can validate at any time in between as well. As I said, the data path is completely unchanged for virtual volumes. Where you're using a SAN now, virtual volumes will still use that exact T10 SCSI data path. And if you're using NAS-based storage, virtual volumes uses NFS mount points and standard NFS commands to access it. So although you'll hear about these protocol endpoints, and they may seem like something new we're introducing, it's really just a neutral word that we tried to pick to represent both the LUN access points on SAN-based storage or mount points on NAS-based storage. And we wanted, because virtual volumes works the same basically whether you're going over NAS or SAN storage, we wanted one word that could represent these access points, and that's all it is. So, the VASA provider. The VASA provider is the key agent that represents the array to vSphere, and it tells vSphere everything about the particular array's capabilities, and that's why it's developed custom by the storage vendor for that particular array. It presents the SPBM capabilities. It is the receiving point for offloads. Pete mentioned snapshots, clones. Instead of doing those operations through the vSphere side, those are now done by commands handed to the VASA provider. And the VASA provider has an interface, a private interface into the array to let it manipulate the storage on the array side. So that VASA provider can actually run on the array in some instances. That's a design choice that partners make. And that has advantages. You can take advantage of the controller failover that's already built into most arrays. Or you can be off the array, and that has other advantages. You can apply vSphere HA to it, or even FT if you want to, back it up, provide those kinds of things.
Yeah.
So,
yeah, the VASA is vSphere APIs for storage awareness. So the very first version was just basically very informational. Hey, this is what's going on. But now with virtual volumes, it's vSphere APIs for storage management. But VASM is not very pretty to say. So it's still VASA provider for those of you that don't know.
And so both ESX and VC connect to the VASA provider to do certain things. For provisioning, for offloads, for capabilities, for policy management, and for binding and unbinding virtual volumes for access, as we'll see later. That's all done through the VASA provider, and so that's why everybody talks VASA to the VASA provider. So the other thing I mentioned are storage containers. And storage containers are the way you present storage out of a vVol-capable array. And the thing to remember about storage containers is they're logical constructs that are created where you want to, as storage administrator, apply some limits. So they don't correspond to something physical on the array. There's not a RAID 5 storage pool or a LUN or anything like that that corresponds one-to-one with the storage container. And that's one of its main advantages. In fact, you can mix different kinds of storage in a storage container. And you can, that way, give a group like marketing an entitlement to 2 terabytes of capacity storage and a terabyte of fast SSD-based storage, and it can all be presented in a single 3 terabyte container. And once you've, as storage admin, created that storage container, the vSphere admins can go off and apply the policies to the VM and have those VMs created as vVols using the right kind of storage. And we'll talk later about why that's actually a real advantage. But the main thing is the storage administrator creates these storage containers to apply the limits that they want to apply on the abilities of the vSphere administrator to allocate things there. And there can be, for that reason, multiple storage containers per array. That it's possible to present all of the storage in the array in a single storage container. I don't believe anyone does that right now. Typically, you would set up different storage containers for different groups that you work with. And that could be marketing, development, HR. That could be customers A, B, and C. That could be different sites that you work with, or whatever makes sense as a storage administrator to apply boundaries. That's what corresponds to storage containers.
Yeah, and the customers I've spoken to, I've seen both. I've seen customers that are actually just having one storage container, but it's typically the same folks that are still having one data store for all classes of service. And so they throw all their VMs into one bucket, and then they have to, they have IO blender because some VMs have more performance needs than the other, but it's all sitting in the same data store. So with virtual volumes, that goes away because of the fact that even though they're all still in the same data store, they're getting different classes of service based on policy management. We'll show you in a little while what that means. But yeah, I have seen some folks that are still just using one storage container tied to one data store because it's no longer, bound to the fact that you have to have the exact same class of service in that bucket, that storage container bucket.
And you mentioned the IO blender effect. That's one thing that goes away because one of the advantages to the storage administrator of introducing virtual volumes is that the storage array gets visibility into what the individual virtual disks are that are in use in the environment. So what was previously just this ill-defined stream of I/O requests to a LUN where all the blocks looked alike and the storage array had no idea whether a given block was metadata for the file system or important data out of your database or something that had to be accessed quickly or anything like that. There was no differentiation. But now the array sees individual streams of I/O requests coming to individual objects, and it can do more intelligent caching. It can provide SLAs that vary from one virtual volume to another. So after the storage administrator has sort of set up the boundaries and the storage admin and VI admin, which could be the same person, have sort of agreed on what kind of storage is necessary and how much of it should be set aside, there is a data store created in vSphere that corresponds one-to-one with that storage container. So you can think of the virtual data store that's created in vSphere as synonymous with the storage container on the array side itself. And as you, as vSphere administrator, go create VMs, there are corresponding virtual volumes created on the array side. And so both sides, storage and vSphere, have the same view of growing storage consumption and insight into which virtual volumes make up which VM. So again, if you as storage administrator are looking at some high I/O load suddenly appearing, you don't have to guess which of the 100 VMs on the LUN is somehow getting hammered and needs to be throttled a bit. You can go down and look at which individual virtual volume is being hit, trace it back immediately to the VM that's the owner of that, and go find the VM owner to see that something's going wrong and needs to be fixed. So there's a level of insight at the storage level that you get from abstracting virtual disks as objects on the array, and there's other power as well. So we've already hit many of these points, but a quick comparison between LUNs as you have them today with a VMFS file system on it and storage containers. The big one is that all the storage associated with a LUN is fixed, it's uniform, and the array has no insight into what's what. The array has no idea how these blocks are different. Everything is managed in-band, and there's reads and writes requests being sent to it. The storage container, on the other hand, is first of all sized to the limit that you want to apply. And unlike a LUN, where if on day one you said, I need 2 terabytes of storage, and then a year later come along and said, well, it wasn't 2, it turns out it's 2.5. Now you have to go create another 500 gigabyte little LUN somewhere, and now you have forever after one more LUN to manage and one more data store to choose from, and you have to decide which data store you put it in. Since these storage containers are just logical constructions that are made on the array side, it's easy to expand the entitlement a little bit and go from 2 terabytes to 2.5 terabytes or whatever is appropriate. And it's just a change that takes effect immediately. You still only have one storage container, and on the vSphere side, you still only have one data store, but now you have raised the limits in a little bit on what you want. So as somebody put it yesterday, they were really excited to see virtual volumes because it finally let them do self-service for the vSphere administrators without worrying that some vSphere administrator was going to create 100 LUNs out of the blue or consume all the storage in some critical storage pool or something like that. Virtual volumes with the storage containers lets them apply guardrails to the things that the vSphere administrator is otherwise free to do with. So you don't have to get involved in every single discussion about a little bit more storage of some type or another, and you don't have to set up multiple types of storage for every single SSD, spinning disk capacity, intermediate that you want to allocate. You create one storage container for the group you want to manage. You set the content, you set the limits. That's the limits that are enforced.
It's always funny having conversations with storage teams, and it's like you're in the middle of a fight, a family feud. The storage teams are always like, I don't want my virtual administrator to have this much power. I don't want them doing all these snapshots. They're going to blah, 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 blah.
And you talk, my array.
And then you talk to the virtual administrator. It's kind of like the younger brother. He's like, these storage team won't let me do what I want to do. So virtual volumes kind of, it makes your family a lot happier.
It's a good way to mediate it. So when you look at what a VM looks like with virtual volumes, there's actually a couple of different virtual volumes that are created for every VM. It starts with a config vvol, and there's one of those for every VM. And we write a small file system on that config vvol, and that takes the place of the home directory that's otherwise there for every VM. So that's where the VMX file lives, that's where log files go, that's where the descriptor files exist that are always there for virtual disks. And the only difference here is that those descriptor files refer off to other individual vvol objects. And that makes it possible to have typical performance for a config vvol, but a data vvol that it knows has to be heavily cached or something because it's the log file for the database and it needs to have very fast access. Or it's the database and it needs a certain kind of caching or dedupe behavior or things like that. With individual storage policies applied on each individual virtual volume, you can change the SLA for different VMs or different disks within a VM even. Besides the config vvol and data vvols you'll see everywhere, We've also defined swap as a vVol type, and if the VM is powered on, one of those is created in place of the swap file that would normally be created right now. And when you take a snapshot with memory, that creates a special type of virtual volume, but fundamentally they're all individual objects at the array level. We've defined these types to give the array some insight into the type of usage that they might see. A memory snapshot is typically written once in its entirety from beginning to end, and it's not really worth caching because it won't even be read again until the VM is powered back on and restored. And then it'll be read entirely sequentially, so reading ahead is valuable, but caching the pieces you just read is, again, not very helpful. Those are the reasons we define some of these different types. And we have a type other for things that don't need any particular special kind of treatment. CBRC digest disks are created of type other because there's nothing in particular the array needs to do to work with it. So that's kind of the creation of a VM out of a multitude of virtual volumes, each of which has an SLA assigned in the form of a storage policy.
Yeah, kind of, traditionally with VMFS, there's, you have LUN limitations, and so that was always sort of a factor. With virtual volumes, you're not going to run into LUN limitations, but you do have to consider the object count for your environment, because every virtual machine is going to have a minimum of 3 virtual volumes, but potentially 5, 6, and depending on how many snapshots you have, could have 8, however many, virtual volumes tied to that, and those are all individual objects. So depending on the size of your environment, you may want to look at, and each storage vendor has different arrays that have different object limitations, and so you're definitely going to want to look into that with your individual storage vendor to see what the object count is for their arrays.
Yeah, that's an excellent point. And with virtual volumes, we've worked hard to encompass all the differences between various different arrays. They can all present different capabilities, and we let you write storage policies that are specific to that vendor. And different limitations may apply. Some of them may be limited in the number of containers they have. Others may have limitations in the total space, or in, as Pete said, the total number of objects that can be created. And then it's important to remember that a given VM will translate to, half a dozen easily virtual volumes. The thing about these different vendors, and all of them using the same mechanisms that we've defined, is actually another benefit of using a virtual volumes approach, because with SPVM you can define a single storage policy that is something like, say, this is what a development VM should have, or this is what a VM in staging should have, or this is what a VM in production needs to have. And that latter may now, for instance, include replication, because you need your mission-critical data to be replicated automatically. A single storage policy can encompass all the different ways that on all kinds of different arrays that SLA can be met. So if you have a NetApp virtual volume array, maybe you want to control dedupe. If you have a pure virtual volume array, you may set different parameters, and you may set the QoS or something like that a certain way. If you're using vSAN, which also uses the same SPVM mechanism, maybe you set the number of copies that are desirable of the object. And so this one storage policy production may encompass all the different ways that you need to configure the SLA on a given object. But to the vSphere administrator, it's all just production. And the value of having a storage container that has multiple different types of storage in it is that as an application goes from development to testing to staging to production, you shouldn't have to migrate that VM from different data stores to different data stores to go from the one that is cheap to the one that is faster and has some SSD backing to the one that is replicated. That should all translate to changes in the storage policy applied to the virtual machine. And that's what you can do. So you can start a machine off in development, and as you go to testing and staging, apply a different storage policy to the VM and let the array worry about meeting the new SLA without you copying the VM around explicitly.
Yep.
So protocol endpoints were the other thing we mentioned. And protocol endpoints, as we said, are the destination points for I/O in a neutral way. On SAN, that's a LUN. And if you look at the low-level view from vSphere of a SAN system with virtual volumes, you won't see the individual virtual volumes. All you see is the protocol endpoint LUNs that are defined there. And we've worked with T10 to define a special notion of a conglomerate LUN, and that's a bit that's identified. So when the PSA storage stack sees vVol LUN, it knows that it's a protocol endpoint LUN. And in fact, it uses that to be careful to only route traffic to that LUN through adapter paths that have said that they can properly pass the secondary LUN ID that we use on SCSI to an array. And in fact, if you have protocol endpoints LUNs that you've mistakenly presented through adapters that don't support vVols, you'll see a message log that says there's a protocol endpoint LUN, but the adapter isn't capable of doing virtual volume I/O, and so we're going to drop that path and only route the I/O over paths that properly pass on the secondary level LUN ID. That's the mechanism we use on SANs to distinguish which virtual volume is being identified for the particular I/O command. So if you're doing a read on a SAN virtual volume, the read, if you look at the SAN level, is sent to the protocol endpoint LUN, but there's a small extra descriptor in that CDB that indicates which virtual volume on that array is the actual target of the read. And that association is actually temporary, and we'll talk in a minute about how that's done. So when you look at data stores currently, they combine two functions into one. Right? They're the actual repositories of your data. They really are where the storage lives, and they are where you address commands. And with virtual volumes, those two are broken apart. The storage itself is provided by virtual volume objects on the array. The addressing of the I/O commands is done through protocol endpoints, and so that's why those are there. So, as we said, on NAS storage, a protocol endpoint is a mount point,
yep.
And on SAN, it's a LUN. So bringing it all together, when you go to create a VM, and as vSphere administrator, you're creating VMs, you're setting virtual disks, and you pick a storage policy for each one. That's the same you're doing in the UI. Under the covers, those commands are translated to provisioning requests to the array sent to the VP, and we associate the storage policy and some of the parameters of the virtual volume that you want to create, what type of virtual volume it is, how big it is, which VM owns it, things like that, to the VP. And the VP, using whatever interface it uses to talk to the array, that is private, creates the objects on the array side and associates the SLA that you specified in the form of the storage policy with the object there. So that's how what is a virtual machine with a couple of virtual disks in vSphere translates to a handful of virtual volumes on the array side with a particular SLA defined for each one that the array knows about and the array can maintain and you can validate. So besides the creation and deletion that we just talked about, because deletion is also done through the VP where you just tell the VP that you're done with this virtual disk, which by the way is another advantage. The array knows immediately when a virtual disk is deleted, and so if you have an expensive all-flash array, that's effectively doing an unmap for the whole thing instantaneously, and all that flash storage that you have is immediately reclaimed on the array side. In the I/O path, we also pass unmaps from the VM straight through to the array, by the way. So there's no VMFS in between that imposes additional granularities or additional operations. With 6.5, it will automatically do unmaps at a certain rate. But with virtual volumes, the unmaps go straight from the guest OS to the array where it can take effect. But I want to talk a little bit about how these protocol endpoints are actually taken in use. And so besides the creation and deletion, when you power on a VM, the ESX host talks to the VASA provider to request access to a certain virtual volume. And it uses the permanent virtual volume unique ID to identify the virtual volume it wants to communicate with. That is a prompt to the VP to talk to the array to set up a particular protocol endpoint, and that's a choice made by the VASA provider. So the array can do a certain amount of load leveling among the different protocol endpoints it may present, because there can be more than one, although some designs work perfectly well with just one. But the array picks a protocol endpoint, and the array picks a secondary level LUN ID to associate with that I/O stream, and from that point on, all of the I/O that the VM does to the virtual volume disk go through that protocol endpoint with that secondary level LUN ID identifier. And when the VM is powered off, that path is no longer necessary, so we send an unbind request to the VP, and that tells the array you can free up that secondary level LUN identifier to use it for another connection later. And the next time you power on the VM, it may have a different secondary level LUN ID. And that's how virtual volumes actually get used through these protocol endpoints. So, Pete?
Yeah. So it's funny, like, it's been around for a couple of years, as we mentioned, and a lot of folks, even internally for a while when I first came to VMware, I would say, like, yeah, this is vVols, I've heard of it, but you know, why would I change? Is it really worth it? What's the big difference between just being on vVols or just staying in what I'm doing with VMFS? You know, status quo is sometimes your biggest enemy. And, you know, there are a lot of different ways to explain this. I think one that I've been using lately that sort of at least helps it stick a little bit is I really do think that virtual volumes are simpler, smarter, and faster. And so I'll start with the simpler. LUNs suck, and they're for a lot of reasons that Patrick has already mentioned. But the fact that the logical versus physical, which we've already covered for sure. But the other one is the retail versus wholesale. Just from a management perspective, having to spin up a LUN dedicated to, you know, one particular workload, tying it to a data store, then, oh, okay, I ran out of room, let me get another LUN, and then now I need to assign the exact same characteristics as my first LUN, and then I'll get another one and have a cluster of LUNs, and there's a lot of human input managing these LUNs to create. That's kind of a retail model. Versus the wholesale model, which is, hey, I'm going to, on day 0, define this storage container, set the parameters that I can do. The virtual administrator is going to create some policies, and that's it. Every time a VM is spun up and chooses that policy, it's already going to have the characteristics that I need in it. I don't have to worry about, you know, recreating the exact same thing every single time. So it's kind of a wholesale versus retail model. I think that is one of the reasons why it makes it a lot simpler. The ability to change the policies, you know, is, you know, if you've got it, like Patrick was mentioning, you've got a test and dev workload. Okay, I want to move this to production. Having to migrate that to another data store that is completely gone with virtual volumes, because it's essentially just changing the policy on the VM and moving it. And the only thing that's going to happen is if it's just a class of service like QoS or changing some other policy, replication or whatever, there is no migration whatsoever. If you're moving from one disk type to another, it's going to do the storage vMotion on the background for you. So just a much, much simpler way to manage your virtual infrastructure.
And just to be clear, it's the array doing the migration of the
Correct.
VMs, right, the virtual volumes, not, you know, vSphere somehow getting involved in the background.
Exactly. And so walking through how that would look, the storage, day 0, the storage administrator would then create this storage container and publish sort of what capabilities that array has. And, you know, every array vendor has different classes of service that they are offering. You know, NetApp has a list of, you know, stuff like, you know, deduplication, encryption, or whatever. Pure's got some great replication going on. Nimble, fantastic, you know, all types of things. SolidFire has a fantastic QoS. So HDS, EMC, all have different characteristics that they're using. And that's kind of the cool thing, because these storage vendors can then be creative and innovative and put what they want to put in that in the policies to set for the virtual administrators. So they publish those, but then the virtual administrator, once he's enabled the VASA provider, he then starts creating those individual policies. Right? Now, you can set them however you want, but for a simple example, test, you know, development, staging, production. And those would have slightly different configurations on the classes of service that I want to use as I provision virtual machines. Right? So, one note, I haven't spent a single megabyte yet of disk space because I've just created some policies. I haven't pre-allocated any space, and now I'm going to start. So I'll create a virtual machine, and as I assign those individual policies to those, the virtual volume objects get created natively on the array. And the best part about this is you can never put it on the wrong storage, because if I say it has to be this production environment, it has to be this media that has all these parameters on this policy, it's only going to show me a data store on my array that can meet that policy requirement for you. So it's a much, much you know, simpler but also more intelligent way of managing your infrastructure, because you know you're always going to provision with confidence that it's on the right class of service.
And that's something you can check for compliance later. If you provision storage with an RPO that you specify of 5 minutes, and then the storage changes to change the RPO to 10 minutes, the next time you check compliance, it's going to tell you, hey, what the array is providing you is actually not in line with the SLA that you specified, so go have a talk or change the policy, or, right? It's all explicit.
Yep. Yeah, and then the smarter part, same thing. I'm making sure that when I create, I've got the visibility into the array now. I don't have to guess, or even if I'm doing both, like a lot of you are, I don't have to go into the array and look, okay, what are the capabilities of this LUN or whatever. Now, I just manage everything inside of vSphere. I've got my policies, I've set it up. It's just a smarter way of doing it. The array owns the actual virtual volumes now. These objects are natively on the array. So anything that happens, if I'm creating a clone, if I'm creating a snapshot, vSphere is not involved. It's just a complete array action. So like we said, every storage vendor has different capabilities that they can present to the environment. These are just a couple of examples. Like you may have, some environments we talk to have like just 3 simple policies. Some have like 15 different policies for all the different levels of service that they want to apply. And so, it's really a choice for you to decide how many of these policies, but you've got that ability to create different classes of service, these different storage policies, and set them once, and then make the changes to your virtual machines as you need. Any change to a policy for a virtual machine is a non-disruptive change, and so it's just a much, much smarter way to manage your virtual infrastructure.
And actually, that's one of the things that has somewhat surprised me about the implementation of virtual volumes in the field. We had no idea what capabilities people were going to present for their arrays. And I've seen arrays, for instance, that present a monthly charge in dollars for a capability for the kind of storage you allocate. So you can provision storage and say, I'm ready to go whatever the fastest is for up to $200 a month or whatever, and provision your storage that way. And that's perfectly reasonable in the virtual volume model, where everything is just an abstract capability of an array. And so there's all kinds of different capabilities that the array can present, and whatever makes sense from the array side, you can consume in the policies that you write.
Yep. And so one of the things that's also incorporated inside of your policies is the ability to do array-based replication, as we talked about. But creating these, and there are different ways depending on your vendor how you want to do that. You can create in advance replication groups, or you can just let when you're provisioning a virtual machine, let those get provisioned, the replication get provisioned for you automatically. But we've introduced this idea inside of the VM storage policies, this idea of storage policy components. So now, instead of statically just tying that replication into individual policies, like we said earlier, we've got, testing, staging, production. Instead of putting that replication policy inside of the testing, I can actually assign that a little bit more globally. I can say, I've got a testing policy. I create a VM, I'm going to assign the testing policy. Oh, but I'm also going to assign some replication. That's a component. You can also do that with, say, encryption, for example. So that same replication or encryption policy can be assigned to multiple virtual machine storage policies. So if I have a replication that's daily, for example, I could assign a daily replication policy to my gold, to my silver, to my bronze policies. And so I only configure the replication policy once, as opposed to having to do it individually for every policy that I own.
Yeah, you mentioned encryption. That's an excellent example of that, because you may be required to provide HIPAA compliance, for instance, with a certain level of encryption. You don't have to worry that all 3 different policies that you have for production applications have the same correct type of encryption applied. You can define the proper encryption once as a component, and then use that component in each of those 3 policies, and you can be assured that all of those storage policies are going to meet the same HIPAA compliance that you're required to provide.
Yep. And so there's just another example of actually creating the virtual machine. When you're going in, you're choosing your policy. In this example, my policy, I can't see the screen here. I've choose a policy. This one has some QoS settings, and then on the very bottom is where you add your component, and you can choose your replication. And as you can see in this example, there have been 2 policies already set. I can replicate to Anaheim, or I can replicate to Boulder, for example. So you've set your replication groups. As you provision VMs, you can just say, okay, this is going to be for this. I'll choose this replication policy and decide where it's actually going. And so Pat's going to talk a little bit about why virtual volumes are a little faster than VMFS.
Sure. Well, there's 2 main reasons why it's faster. Because the array manages all these objects natively, we can offload all kinds of operations to the array itself. And let's face it, these things go the fastest the closer you can get to the actual data. The slowest is to copy it into the host and to copy it out again somewhere else. Faster is VAI xcopy, where you ask the array to copy a certain bunch of blocks from one place to another. But you just can't beat the speed of asking the array to make sure that I like another object that's just like that object. It can do some quick metadata manipulation and create a clone of a virtual object in much less time than you could even issue the VAI calls to make a copy like that. And the same applies to snapshots. Arrays have very sophisticated snapshotting capabilities available at the LUN level, and many of you are probably using that when you're doing backups or things like that. Those same capabilities are now available for virtual volumes. So when you create a virtual volume snapshot, and we'll look at that in some more detail in a minute, that gets offloaded to the array. And so the snapshot is created quickly, and the array's native abilities to do copy on write, for instance, or other mechanisms can be applied to managing those snapshots. So it's just absolutely the fastest to let the array do it natively. And the other thing we hit on, since storage containers can represent different classes of storage, where before you had to do explicit storage migrations and copy data from one set of LUNs to another as they move from the various stages in their life cycle, with virtual volumes, you can just change the storage policy on an existing VM, and the QoS or the SLA can change on the fly.
So one of the questions I get a lot, and maybe you can answer it, Pat, is if I'm using virtual volumes, do I still need VAI?
VAI will still help with migrations in and out of the array, so it still applies there. But for most things, we don't use it anymore. So xcopy is really not necessary because we try to avoid copies. ATS, would still be used on the config vvol actually, but wouldn't be used because there isn't a file system on the Datastore or things like that. So yeah, there's still a role for that, but it's not as prominent or important anymore. We talked about snapshots, and look, you're all familiar with redo log-based snapshots. And as you stack up snapshots and stack up more redo logs one behind the other, with every one that you stack up, the data that you want to go read has to be checked first in the first redo log to see if the latest copy may be there. If it isn't there, you have to go look in the next redo log to see if in between the time since the last snapshot it was written there. And if it isn't in that one, you have to go to the next one. And if it isn't in there, then you finally go to the underlying disk and read the block that never changed at all. So you can imagine why we found, for instance, in testing, that by the time you have 4 snapshots, redo log-based snapshots stacked up like that, you're down to 10% of the IOPS that you used to get out of the disk before. And what's even worse, when you go to delete these snapshots, you have to go write the data that you first wrote into the redo log already all over again into the underlying redo log. So you start this process, and all the while the VM is generating more data, you're trying to collapse these redo logs, you're repeating I/O that you already did, and then finally you're rid of the snapshot. So small wonder they're not very popular. On virtual volumes, it's very different. You create another disk when you can take a snapshot. But then we do what we technically call a swizzle between the two disks, so that I/O that is directed at the snapshot actually goes back and writes on the same original object all along. And we are not involved in maintaining the snapshot view of the data. It's the array's responsibility. So reads still go directly to the object that you were reading with. And if you make writes, the array is smart enough to know that that snapshot somehow needs to reflect the original view of the data, and the real virtual disk needs to be updated with your newly written data.
Yes.
So you can see that that's a lot faster already.
Yeah, and the snapshots will still show up if you're inside of VMware and you want to manage and revert to an individual snapshot inside of VMFS. You still see the tree of snapshots that you're creating, so it is technically still managed inside of vSphere, but they are just array-based snapshots that are still found in your array software.
Yeah, that's a good point, because the distinction between virtual volumes and other types of volumes, be they on VMFS or NFS or other storage, exists at a very low level. So for most operations that view the VM as a set of VMDK descriptor files that they can reference and know that a snapshot is created, there's another descriptor file that's created, they can go read that, things like that, all still works. Virtual disks are still virtual disks. The representation is still the same. Disk lib still works as it does. The distinction is really at a much lower level and usually doesn't come into play, so there isn't automatically some concern for compatibility or things like that. The software that manipulates virtual disks in the abstract still manipulates those same virtual disks in the same way. So when you get rid of a snapshot, you just throw away the snapshot copy that was made, and that's it. There's no need to do any additional I/O. You've just thrown away data that you no longer care about. And when we go to actually revert to a snapshot, that too is offloaded to the array. So we start by creating a fallback point in case anything goes wrong, and then asking the array to copy the data that was in the snapshot into the actual underlying disk, which again can be as simple as a metadata operation on the array side. And when that is done, we throw away the snapshot, throw away the fallback point, and you've reverted to a snapshot. Much faster than you could ever do it before.
Yeah, and also for backup vendors like Veeam, for example, and other, you guys are, they're seeing that their restore times are significantly faster because the software is using VADP. Right, so as long as you have a backup vendor that's actually using VADP, it's going to execute a VMware snapshot, which traditionally would be a VMFS snapshot. But when you're using virtual volumes and you're in Veeam taking a backup, it's going to do a vVol snapshot and offload that to the array for you. So we're seeing a significant decrease in times to do backup and restores, even with some of our backup vendors like Veeam.
Yeah. So not only is taking snapshots faster, and not only is deleting snapshots faster, but while you have a snapshot in place, you're not paying a penalty for that snapshot being there. So you don't have to start playing games like snapshotting a VM and then snapshotting the LUN that it lives on and then mounting and resignaturing that to make it accessible and then going on and accessing the VM, just so that, God forbid, you don't have a snapshot in place while you're doing I/O on your actual VM. You can actually just create a snapshot, back up the snapshot, and throw away the snapshot with no penalty whatsoever. So virtual volume replication is an important new technology that we've introduced with 6.5. We realized when we first introduced vVols in 6.0 in early 2015, really serious enterprise tier 1 application use would want to be able to replicate the storage, but it was just more than we could bite off for that release. So we had to leave that gap in place. With 6.5, I'm happy to say, we've really filled that hole. And besides changes in the SPBM user interface that now separate out some of these groups of capabilities to include replication, there have been extensions to the VASA protocol that is the interface to the VASA provider to not only convey which groupings of VMs should be treated together, but also controlling the actual failover. So when you set up an array that has replication relationships between arrays in different cities, let's say, you can specify the replication parameters for a virtual disk in the storage policy itself. So when you apply a storage policy that you've written to include replication, you get to pick which replication relationship you want to use. And that is all driven by data that vSphere has dynamically derived from the array. So there are new VASA API calls that tell vSphere what these islands are that replication exists between. We call them fault domains. That may not be strictly, literally, exactly the hardware that will fail together when something bad happens, but these fault domains are the endpoints for replication relationships that we call replication groups. And replication groups serve two critical functions. They define the consistency requirements for the virtual volumes that are in there. So the array will maintain write order fidelity within a consistency group to make sure that the replica that exists on the other side is at least a crash consistent image of the data on the source side. And those replication groups become the granularity for failover operations. So when you do a test failover or a failover, you're not failing over a complete storage container with all of its content. You could be failing over as little as one virtual machine that is part of that replication group. So as you create virtual machines, as you apply policies with replication relationships, it either uses predefined replication groups, or in some cases, if the array is capable, we'll create a brand new replication group just for use with this VM or subsequent VMs that may want to take advantage of it. And that means one VM could be replicated to New York, and the next VM could be replicated to Miami, just by the choice of replication group that is specified with the storage policy. And of course, you can have different replication groups going to the same destination with a different SLA. There may be production data that is replicated much more often than other data or things like that. So these replication groups can be different for the different SLA or because of the different granularity of failover that you want. You may have a set of accounting VMs that you want to be able to fail over independently of the marketing VMs, which you may or may not choose to fail over, and things like that. So replication groups are a new concept. They are the unit of consistency and the unit of granularity for failover operations. So in the user interface, all that boils down to one extra pop-up that shows up when you apply a storage policy that has replication parameters defined. And because the storage policies are now stratified with different groups of capabilities grouped together, we can tell when there is replication specified in a storage policy. And we interrogate the array, ask it which replication groups would be compatible with the SLA specified in the policy, and that list of replication groups is presented for the user to choose from, or if the array is capable, an additional option, automatic, is specified, which creates a brand new replication group. So after all of that setup, all that shows up is one extra pop-up when you define a storage policy that has replication defined.
So you've replicated your data, but you want to restore it. How many folks in here are using Site Recovery Manager? Okay, so for those of you that are using Site Recovery Manager, you can still use vVols, but it's going to be through vSphere replication.
Right now.
Yeah, and this is something that we're working on. We're hoping that the SRM team is going to have some answers for us in terms of getting replication supported with array-based replication supported with vVols. But today, if you are replicating and you do want to do some failover, the workflows for SRM, very similar workflows, can be done through various automation options. Power CLI is certainly one of them. There are several commands that can do the discovery, the test workflows, the failover, the failback. All of those traditional SRM type workloads can be completely automated. And what's more, a lot of the vendors that are supporting array-based replication have already done the work of creating some sample scripts and uploaded, whether it's in GitHub or on VMware's blog called Virtual Blocks. We've got a ton of examples from like Nimble and Pure and HPE, et cetera, to show you what it looks like to actually do array-based replication with virtual volumes.
You recently published a blog post with HPE about how to script it soup to nuts, right?
Soup to nuts, doing tests and everything, yeah.
So, yeah, not coincidentally, what you see in the middle is the new APIs that we defined in VASA to control replication. And they very closely mirror the interfaces that SRM would use today with LUN-based replication through an SRA to control the replication there. And so there's commands to synchronize the replication, do failover, test failover. And because a lot of people use Power CLI to script their replication so that they can be sure that it's executed the same way every time it's tried, we've introduced Power CLI commandlets that let you issue these calls. And so you can completely script your replication with virtual volumes using Power CLI, and Pete's blog has an excellent example of that.
Yep.
Want to sum up?
Yeah. So quick summary and roadmap. And the good news is the product manager for vVols is in the room. And so I'm going to talk about what is coming up, and then we can talk about what I'd love to hear input from the audience in terms of what you guys think should be available next in the next version of virtual volumes. But I will say that we're targeting for vSphere 6.7 just a few minor uploads. Virtual volumes in general, I feel like we've reached a piece where it's pretty enterprise ready and is with the exception of the SRM support, which we hear very loudly, we're pretty much happy with where we are, and a lot of the different vendors are now getting certified for VASA 3.0. So a couple of the ones that we're going to be focusing on for vSphere 6.7 is IPv6 support, performance parity with VMFS, and then some support for MSCS on vVols. And as I mentioned, we've got a ton of partners that are involved with virtual volumes. We're getting new partners added a lot. Just recently, we had 2 partners within the last month that have been certified on our HCL. So if you're interested in vVols, for sure, I can't think of one vendor specifically that's not on vVols for at least one of their arrays, but there's a large community of storage vendor support for virtual volumes. So call to action here for you folks before we start taking some questions. If you want to learn more about vVols, you've got some options. We have a site at VMware called storagehub.vmware.com where we park some content around vSAN as well as virtual volumes. We have a podcast. I hear it's really good. There's a couple of guys that do that at VMware. One of them I think is in the room. And then also there's a hands-on lab as well that you can download or actually work with virtual volumes. There's a couple of different vendors out there that are on the hands-on labs to give you a chance to spin it up and test it for yourself. So these are just a couple of options for you guys to see what you want to do next with virtual volumes. We are going to stick around for questions, and so we want to, 1, thank you guys for coming, but 2, please fill out the survey. And if this was a good session to you, my name is Pete Fletcher. If you didn't like it, my name is Patrick Dirks. And now we'll stick around for some questions. Come up to the mic if you can. We'd love to hear your questions. If not, we'll close it depending on who comes up, and then we'll just do one-on-ones. Thank you for coming.
We'll actually be happy to